Here's something a little magical. You take a text file, say a megabyte of English, run it through zip, and out comes a file a third of the size. Then you unzip it, and you get back every single byte exactly, not one character changed. Nothing was thrown away, yet the file got dramatically smaller. So what actually happened in between? How can the very same information take up less space? By the end of this, you'll understand the two ideas behind almost every compressor you have ever used. First, a fork in the road. There are two families of compression. Lossless, where you can rebuild the original perfectly, bit for bit. That's zip, gzip, and PNG images. And Lossy, where you deliberately throw away detail you won't notice to save much more space. That's JPEG photos and MP3 audio. For most of this video, we'll stay in the lossless world, because that's where the genuinely clever ideas live, and we'll visit Lossy right at the end. Every lossless compressor lives or dies on one word: redundancy. Real data is not random. Text repeats letters and whole words. Images have big patches of the same color. Logs say the same thing over and over. Compression is simply the art of noticing what repeats and then spending fewer bits on the parts that are common or predictable. If the data truly had no pattern at all, there would be nothing left to squeeze. There are two timeless tricks for spending fewer bits, and you'll meet both today. The first, give short codes to the things that happen most often. The second, when something repeats, don't store it again. Just point back to where you already saw it. Almost every real compressor, from zip to PNG, uses both of these together. Let's take them one at a time, starting with shorter codes. Start with how your computer normally stores text. In plain ASCII, every character takes the same 8 bits. The letter E costs 8 bits, and so does a rare Q or Z. But that's obviously wasteful. In ordinary English, E shows up constantly, while Z barely appears. Giving them the same price is like charging the same postage for a postcard and a piano. So what if the most common letters were simply cheaper to store? This idea is older than computers. Look at Morse code. The letter E, the most common in English, is a single dot, the shortest possible signal. A rare letter like Q is a long dash dash dot dash. Samuel Morse, back in the 1840s, literally counted the letters in a printer's typecase to decide which ones earned the short codes. Frequent things should be short. That instinct is the whole foundation of our first technique, called Huffman coding. Let's make it real with a tiny example, the word abracadabra. Count the letters, and you get A 5 times, B twice, R twice, and C and D just once each. 11 characters in total. Stored the normal way, at 8 bits each, that's 88 bits. Even if we were clever and used a fixed 3 bits per letter, it's 33. Watch how Huffman does far better by letting the letter A, which appears the most, become the cheapest of all. Huffman builds a tree from the bottom up, and the rule is beautifully simple. Repeatedly take the two least frequent items and join them under a new parent whose frequency is their sum. So C and D, the two rarest, pair up first into a little node of weight 2. Then we keep merging the two smallest available nodes. R joins that pair, then B joins them, and finally the heavyweight A joins everything at the very top. One tree with every letter resting at a leaf. Now label every branch. Say a left turn is a 0 and a right turn is a 1. To read off a letter's code, you simply walk from the root down to its leaf and collect the turns. Because A sits right next to the root, its code is a single bit. B is 2 bits, R is 3, and the rare C and D are 4 bits each. Exactly what we wanted, the common letter got the short code, and the rare ones pay the price. Add it all up. The letter A costs 1 bit 5 times over. B costs 2 bits twice. And so on down to C and D. The whole word now fits in 23 bits, down from 88. That's the same 11 characters, fully recoverable at roughly a quarter of the size. And notice, we didn't lose a thing. We just stopped paying full price for the letters that show up all the time. But wait. If the codes have different lengths, how does the decoder know where one ends and the next begins? There are no commas in the bit stream. The answer is the quiet genius of the tree. No letter's code is ever the beginning of another letter's code. Since A is one specific bit, nothing else is allowed to start that way. This is called the prefix property, and it means the bits are never, ever ambiguous. Decoding then becomes a walk. Start at the root, and let each incoming bit steer you. left or right, until you fall off the bottom onto a leaf. Emit that letter, jump straight back to the root, and continue with the next bit. The stream of bits simply becomes a stream of turns through the tree, and out pops the original text, one letter at a time with zero guesswork. Huffman is actually provably optimal. Given the letter frequencies, no other per symbol code can do better. But that phrase, per symbol, is also its ceiling. Huffman only ever looks at one character at a time. It has no idea that an entire word or a whole sentence just repeated a moment ago. To catch repetition at that scale, we need a completely different trick. The second big idea. Imagine a file that says, the cat sat, the cat sat, the cat sat. Huffman would dutifully hand short codes to the common letters, but it would still spell out that whole phrase 3 separate times. Yet you, reading it, instantly notice something. It's the same chunk over and over. So what if, instead of repeating it, the compressor could just say, see that thing from a moment ago? Copy it. That's exactly what the second technique does. It's called LZ77 after Lempel and Zeev, who published it in 1977. The idea, as you read through the data, you keep a window of the recent past, the stuff you've already seen. Whenever the text just ahead matches something in that window, you don't store the text at all. You store a tiny back reference, go back this far, and copy this many characters. Picture 2 regions sliding across the data. Behind the cursor is the search buffer, everything you've already processed. Ahead of it is the look ahead, the characters coming next. At each step, the compressor hunts through the search buffer for the longest stretch that matches the start of the look ahead. When it finds one, it emits a single token, a distance back to where the match begins, and a length. Then it slides forward past everything it just covered. So the first time a phrase appears, it costs real characters. Those go in as plain literals. But every later copy collapses into one small back reference. That repeated abra near the end isn't 4 fresh letters. It's distance 7, length 4. Point back and copy. The longer and more frequent the repeat, the bigger the win. Entire duplicated paragraphs can shrink down to just a handful of bytes. Every compressor's output is therefore a mix of 2 things. Literals, the brand new characters it is seeing for the first time, and matches, the back references to things already seen. A good compressor is constantly asking about the text right in front of it, have I seen this before, and if so, is pointing back actually cheaper than spelling it out? In real files, surprisingly often, the answer is yes. Decoding is almost too easy, and that is precisely the point. Decompression is fast. You just replay the tokens. A literal, append the character, a back reference, go back the given distance and copy the given number of characters, one at a time. There's even a neat trick hiding here. The length can be longer than the distance, so you copy characters you are still in the middle of writing, which turns one tiny token into a long run. Perfect for, say, 1,000 repeated spaces. How far back should the window reach? It's a genuine trade-off. A small window is fast and cheap to search, but it can only catch repeats that sit close together. A bigger window finds matches across much longer distances, squeezing harder, but every single search costs more work. Classic gzip, for instance, looks back up to 32 kilobytes, a sweet spot that has served the entire web for decades. Now here is where it all comes together. The most famous algorithm in the world, DEFLATE, the engine inside zip, gzip, and PNG, uses both ideas, one after the other. First, LZ77 replaces the repeats with back references. Then Huffman takes that resulting stream of literals and references and hands the most common ones the shortest codes. 2 simple tricks, stacked, each one compressing what the other leaves behind. Is there a limit? Absolutely. Claude Shannon proved there is a hard floor set by how much genuine surprise, how much real information the data actually contains. You can compress predictable data enormously and random data not at all. It's also why you can't usefully zip a file that's already zipped, the redundancy is already gone, so there is nothing left to find. Compression squeezes out predictability, and once that's gone, it's gone. Which finally brings us back to lossy compression. When the data is a photo or a song, you gain another move entirely, throw away detail a human simply won't miss. JPEG drops fine color and brightness variations your eye glosses right over. MP3 discards sounds that are masked by louder ones. That's how a photo gets 10 times smaller than any lossless trick would ever allow. Not by storing it more cleverly, but by deciding some of it was never worth keeping. So what does all of this mean when you actually use it? Text, code, and logs compress beautifully because they are absolutely saturated with repetition. Files that are already compressed, a JPEG, an MP4, a zip, barely shrink at all because the patterns have already been mined out. Giving the compressor more memory of the past generally means smaller output. And it's why everything from your backups to the web pages you load arrives squeezed, then quietly expands the instant it lands. So, strip away the mystery, and compression comes down to two human-sized ideas. Spend fewer bits on whatever is common. And never say the same thing twice, point back to it instead. Stack those two together, and you can fold a file down to a fraction of its size, then unfold it perfectly every single time. It was never magic. It was just a stubborn refusal to waste space,